Let's begin by reviewing what we learned yesterday in the Desmos activity. See if you can fill in the blanks for Theorems 9.1, the corollary, and Theorem 9.2. You should pause the video at this moment. So yesterday we learned that if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So here we can see a radius, and let me draw a tangent. And if this was a tangent line to the circle, then we would have a right angle right here. The corollary that we learned about towards the end of the Desmos activity yesterday said that tangents to a circle from a point are congruent. So here's our point. Here's our points of tangency. These two segments are congruent. And then we technically didn't cover this theorem yesterday, but it is the converse of Theorem 9.1. So Theorem 9.1 starts with knowing that we have a tangent and saying because we have a tangent, we've got perpendicular lines here. The converse goes the other direction. It says that if a line in the plane of a circle is perpendicular to the endpoint of a radius on a circle, then it's tangent to the circle. So in other words, if we have a right angle here, then we know this line is a tangent line. Please flip it over to the back of your handout of notes and try to do this problem. Circles M and N are tangent to each other at point P. So M is the center of the small circle, N is the center of the larger circle. Segments PR and SR are tangent to circle N. Circle N has a diameter of 16, which means its radius is going to be 8. PQ has a length of 3. And RQ has a length of 12. Pause the video for a moment and find these segments. To help us figure these out, I'm going to draw in some radii, or try to draw in some radii. So I know PM and NM are going to be congruent because they're radii from the same circle. And I'm also going to draw the radius from N to S here. So we have right angles at S and at P. And I know this entire length here is 15. So we know that RS is 15. NS is the radius of circle N, and since the diameter of circle N was 16, we know NS is 8. And that would mean that this would be 4 and 4, since NP is also a radii, or a radius, I should say, of circle N. And I'm going to draw in this segment here from M to Q. Notice 3, 4, 5, Pythagorean triple. MQ is 5. PM is 4. And PR is 15. And we have one other segment here, NR. So let me draw NR. NR is this segment here. And if you notice, we have a right triangle where the legs are 15 and 8. And the hypotenuse is NR, and you might recognize 8, 15, 17 as a Pythagorean triple. So NR is 17. You might want to pause the video for a moment so that you can find the notes on section 9.3, arcs and central angles. Now we're going to talk about arcs and central angles. So if you take a look here, I have a circle, circle E, with several radii. And notice that these angles, AEB, AED, DEC, that those angles have their vertex as the center of the circle. This point E is the center of the circle. And when we have an angle where the vertex is the center of the circle and the sides of the angle are radii, we have what are known as central angles. So these are central angles, AEB and DEC. So a central angle is an angle with its vertex at the center of the circle. And the sides of the angle are radii. Now you'll notice we have several curves around the edge of the circle. These are referred to as arcs. An arc is a curve between 2 points on the circle. So here we have an arc AB. So once again, an arc is a curve between 2 points on the circle. And arcs can be different sizes. Some are small, some are large. And we're going to classify these arcs just like we classify angles in a moment. There are 3 classifications of arcs. We have minor arcs, major arcs, and semicircles. A minor arc is an arc that is less than 180 degrees. So for example, AB would be a minor arc. Notice the arc symbol is an arc. BC would also be a minor arc. By the way, if this central angle had a measure of 60 degrees, then the measure of the intercepted arc would also be 60 degrees. And if this arc here had a measure of, let's say, 80 degrees, the measure of its central angle would also be 80 degrees. So minor arcs would be arcs like DC and AB and BC and AD. There are quite a few minor arcs here. Major arcs are those arcs that are more than 180 degrees, greater than 180 degrees. Now, here we have to be careful. We want to make sure we use 3 points to name major arcs. For example, arc ABD would be a major arc because I go A, B, and I'm more than halfway around the circle, and then I go to D. So more than 180 degrees. At C we're at 180 degrees, and then all the way around to D. That gives us more than 180 degrees. By the way, I could have also called that arc ACD instead of ABD. It doesn't really matter which point I name along the way. I just need to make sure I have the beginning point and the ending point and some other point in between. So ABD or ACD, it doesn't matter. Or I could have gone the other way around the circle, DCA. But the important thing is that we have 3 letters to name the major arcs. And we have semicircles. We want to make sure that we use 3 letters to name semicircles. Semicircles are equal to 180 degrees. So you might say, well, why do we have to use 3 letters to name a semicircle? Well, notice here, semicircle ABC and ADC are different. ABC goes to the right and ADC goes to the left. So once again, we need to make sure we name those semicircles with 3 points so that we know which one we're talking about. So make sure you use 3 points to name major arcs and semicircles. That's very important. All right, let's take a look at the arc addition postulate and Theorem 9.3. The arc addition postulate is very similar to the segment addition postulate and the angle addition postulate. Let's see what this postulate says. It says that the measure of the arc formed by 2 adjacent arcs is the sum of the measures of these 2 arcs. Right, that's not very helpful unless we have a picture. So let's draw a picture. Let's put a couple points on this circle. We'll put point A here, B here, and let's put C here. Let's say that the measure of arc AB is 60 degrees, and the measure of arc BC is 90 degrees. What would be the measure of arc AC? Well, because these are 2 adjacent arcs, they share a common endpoint of B, then the measure of the entire arc from A to C would be the sum of the 2 pieces. The measure of arc AC would be 150 degrees. That's the arc addition postulate, just like the segment addition postulate and the angle addition postulate. And let's also take a look at Theorem 9.3. Theorem 9.3 says if the same circle or congruent circles, 2 minor arcs are congruent, then their central angles would be congruent. By the way, this looks like it's a typo, but it's not. It's if and only if. That means the original statement and the converse are both true. But basically what this is saying is that if we have 2 congruent circles here, and if the minor arcs are congruent, then the central angles are congruent. So 90 degree arc, 90 degree arc, 90 degree angle, 90 degree angle. Notice that these circles are congruent because, I should have marked them, the radii are all congruent. So the arcs will be congruent in terms of their length and in terms of their angle measure if the central angles are congruent. So right now you should put away your notes and start working on your assignment.